So yes, good afternoon, everyone. My name is good afternoon, everyone. My name is Jiefei Cao, and I'm from University of Missouri, Columbia. I'm now a third year PhD student in civil engineering, and my advisor is Dr. Frank Shell. I'm sorry. Yes. And today I would like to give a speech on PFAS enrichment in aerosols, since bubbling is a prevalent phenomenon in nature. I like to give my presentation from a start of introduction of PFAS to our experimental setup, and then I would like to share some of our results and our future work. So what are PFAS? PFAS are human-made chemicals with hydro- and oleophobic properties, which let them have a wide applications, for example, in firefighter foaming or consumer products and industrial applications. And because it is resistant to degrade in the natural environment and tend to bioaccumulate in human bodies, it can cause a lot of health effects like low infant birth weights and the immune system problems, as well as the increased risk of high blood pressure, as well as cancers. So as a result of it, there has been regulations for 6 PFAS from EPA. So PFAS have been famous problems for years, and there are huge amounts of PFAS-related study from remediation, occurrence, to the fate and the transport. And for remediation, foam fractation is a new promising treatment technology for PFAS. But does it really remove PFAS or just transfer it from water to the air? And for the occurrence, there have been papers showed that PFAS have been detected in a remote area, even in Arctic. This triggered the scientists a question, is that how PFAS can travel that far? So people start to look at the atmospheric transport of PFAS. And also aerosol as a famous transport media in the air start to arise our attention. And our hypothesis of our study is first, whether PFAS can be enriched in aerosols through sea spray or bubbling, and what will influence their enrichment behavior. And here is our experimental setup. So it is a square tank with an air stone at the base of it to generate bubbles and an air pump to control the bubble flow rate. And we will use an activated carbon sheet to cover the tank during bubbling to capture any aerosols. Then we will use 100 milliliter methanol to extract it before we send it to our LC mass for PFAS analysis. So we will derive the enrichment factor based on the mass ratio, and before each experiment, we will measure the absorbed water volume to calculate the enrichment factor. So here I want to share some of our results. We have investigated PFAS enrichment in 2 water bodies, real water and DI water, from 5 seconds to 80 minutes. So here we need to notice that the axis is in log scale. And although there have been a lot of papers reporting a high PFAS enrichment in aerosols, the time they investigate is usually long, from 16 hours to 30 hours. Our study has found a high PFAS enrichment even at a very short time, even at like 5 seconds. And also from the figure, you can see the PFAS enrichment is highly chain length dependent, with long chain PFAS has a higher PFAS enrichment. However, there is some difference between these 2 water bodies, with the real water showed a more stable trend across time, maybe because of the natural organic matter and electrolytes in the water body. It demonstrates that PFAS stability at air-water interface is strongly influenced by the water chemistry. And we have also studied some profiles of the concentration in the bulk solution. And we found that short-chain PFAS is kind of stable near the unity, showed a minimal loss. Long-chain PFAS are more likely to partition away from the bulk solution and showed a gradual decrease up to 20 to 35% reduction. And the stability in the short-chain PFAS confirms that the observed enrichment in bubbling tests is due to the interfacial behavior rather than the background decay. And then we investigate 3 impact factors: water level, temperature, and ionic strength. For the water level study, we have tested PFAS enrichment at 2 water levels, 7 and 10.2 centimeters. And we found that a deeper water can generate a higher PFAS enrichment. And for long-chain PFAS, the enrichment is sustained across 2 water levels. However, for the short-chain PFAS, the enrichment is transient at both water levels. For temperature effect, we have tested the PFAS enrichment at 2 temperatures, 4 and 25 centigrade. And we find that higher temperature can cause a higher PFAS enrichment. Interestingly, we found that short-chain PFAS showed a much lower PFAS enrichment at a lower temperature. The reason behind it is still unclear. We may need to do some further work, like investigate some the bubble performance at both temperatures to dig the reason behind it. However, it's kind of, it seems like the short-chain PFAS is highly temperature sensitive for the PFAS enrichment. And then comes to the ionic strength effect. So we have tested the PFAS enrichment at 4 different ionic strengths with the calcium chloride addition at 0.001, 0.01, and 0.1 mole. And from the figure, you can see the enrichment of short-chain PFAS is strongly suppressed by the ionic strength. But for the PFSA, as you can see, PFBS and the PFHX, the enrichment is enhanced by the presence of ionic strength, maybe due to the sorting out effect, which will enhance the hydrophobic interaction. Because as we know, PFSA is more hydrophobic than PFCA because of the difference in the functional group, sulfonate vs carboxylic. And then I want to share some of our future work. And we will connect our work with some bubble studies in sizes, distribution, velocity, under our experiment conditions using high-speed camera from Jiefei. He is a postdoc also in our department to derive some conclusions, and we want to maybe dig some reasons behind our findings. And excitingly, our water center has a new instrument coming in, which is QCMD, and we want to use that to measure the rate of PFAS absorption to air-water interface, as well as the rate of desorption, to make a comparison with our developed EFT curve. And we also want to study the interfacial thermodynamics by measuring surface tension isotomes. And after we gather this data, we would like to model the process to see whether it is controlled by kinetic or thermodynamic. And that's all my work. Thank you. Okay, sure.
Yeah, we're well under time, so I'd say we have time for a couple of questions before the next speaker.
So for higher enrichment, that would mean that like more of the mass of PFAS is being lost from the bubbles.
Yes, because the absorbed water volume, like for our experiment, the absorbed water volume to the carbon sheets is really small. So because we derived the enrichment based on the mass ratio, so it's kind of like the concentration multiplied by the volume. So it maybe the mass is not lost. The mass loss is not that big during the bubbling time, because for us, the longest time is 80 minutes. And for some studies, they can maybe last long to 16 or 30 hours, even like in the field study. So yes, the mass loss detected in our study maybe is not that huge. So that's why we have studied the profile of the concentration in the bulk solution, and we didn't see a very huge decrease like across our experiment time.
Thank you.
Yeah.
Anyone else?
So you study about the aerosol generation process and the enrichment, but have you ever collected a sample from the wastewater treatment plant? One specific field is oxygen tank or the aeration tank. When you go there, you will see the bubbling with a very thick layer of holes. Is there any concern on the PFAS enrichment in that form or the health risk workers in municipal wastewater? Thank you.
Yeah, we haven't collected these like maybe real data from the water treatment plant, but it may be a good idea because did you think that because there is already some foam formed in the water, so we can use that for our study? Did you
Wait.
just because that water already contains a lot of foam because the treatment, so you want us to maybe to collect that water for our study to maybe to derive some other finding.
Factor maybe compared to the influence with water, so the PFAS concentration in that.
Yeah, maybe we can do that, but I don't think because I think we have tested in real water because it can represent some like real conditions because we have tested like the natural organic matter, and also there are some electrolytes. So it kind of like mimic the real condition, maybe not seawater, but yeah, we can see some effects of that. Yes.